switch things a little bit here, and so I think some of this could be useful, and talk about offset dishes for EME. I can make this go. No, let me try this. Okay, here's an outline of what I'm going to try and cover. I'm going to talk about first why interested in offset dishes, and one of my interests is getting more EME activity up and getting more activity, and part of that is getting bigger antennas and easy to make antennas. And Yagis are great antennas, but they do take some skill. I like to do things as easy. I don't say you can get something for nothing, but the emphasis here is on doing something very easy. And one way of doing that is to use a technique known as stress dish, and I'll go over that here. And then I'm going to talk about how you can apply the same stress dish idea to offset dishes. And I'll talk a little bit about construction, mounting, and performance. So here we are. The focus here is on 70 and 23 centimeter EME de-expeditions. They're very popular, but you're going to do this, you need portable antennas. And many people in this group, among myself, I will say, prefer to make contacts on CW, though I certainly would not avoid making contacts. In fact, if it's the only way to do it, I definitely like JT also. But to make contacts on CW and to make work very weak signals, small stations, you need more gain. And that's, of course, the name of the game. We're just talking about here if you want to work very far away, real DX, as they say. You need more gain to do this. An issue on 23 centimeters in particular is the fact that most of us use circular polarization. And so when a station comes on with a Yagi, you're throwing away 3 dB of gain. So you like to have a way of getting around the problem of linear polarization. And if you go to a dish, that is an easy way around it. On 70 centimeters, we have a different problem. We have Faraday. And that means the polarization rotates. And people are using linear polarization, but we like to have ways of rotating our polarization easily. And it may not be obvious, but dishes, since you only have to adjust the feed, offer advantage there. So these are reasons to look at dishes as an antenna. Now, this brings us to stress dishes. And I think most of you are familiar with stress dishes. The advantage of stress dishes are that they're very easy to construct, inexpensive, I might say, too. I guess I have that down here. They're easy to construct. They tend to be ideal for portable applications because they're easy to assemble and take apart. They're lightweight, and a factor for many of us is low in cost. Many people's budgets are limited, and they offer the potential of high gain, considering all these other factors. So let's go to some dish basics. When we look at a dish, this happens to be for a 7-foot dish, but the basic idea is the same. People think there's a lot of mathematics to dishes. Very simple. One equation here. X squared is equal to 4py. This is your equation of the curve of a dish, and I've plotted this out here. This shows you a 7-foot dish, and we talk about F over D ratio. This is the focal point distance to the diameter of the dish. And this was set up here, curve is for a 0.55. When we look at F over D, the thing to keep in mind is that the deeper the dish is, the smaller the F over D ratio. So you see people, as they extend dishes and things like that, they get to small F over D ratios. I see people using things that approach 0.2, certainly 0.25, I think a number of people have here. One of the problems is that the smaller the F over D ratio is, the more difficult it is to distribute your energy across the dish. There's no, people ask, what's the F over D ratio? There's no one F over D ratio. It's just what you can illuminate the dish for the F over D ratio you have, because ideally you want to spread your energy uniformly across the dish. But that you can't do practically because someplace the antenna that's feeding this is going to have a pattern that doesn't just shut off. It doesn't go to zero. It continues going, and this is the beam pattern of your feed. So it's the whole name here is to match the feed to the dish reflector. And so, when you get to very low F over D, it becomes more difficult to feed your antenna. When you go to very high F over D ratios, like 0.8, 0.9, 1, you can even go beyond that. Now you need a large antenna to feed. The feed becomes very complicated. And so there's generally some place in between the two. Okay? The stress dish concept is based on a cantilever beam. I think we've all seen, I don't bring any props here, but if I had a piece of a rod here, if I bend that rod, the rod follows a curve. For small deflections, you get a parabolic curve. For larger deflections, you get an approximate parabolic curve. So you have a way of getting a parabolic curve with very little effort, not a lot of skill. All you got to do is able to bend your, I like to call them spokes of the reflector. And as long as you bend them the same amount, you're going to get something that's symmetrical, and that's key. This curve over here shows you some effects, because I said you get an approximate parabolic curve. Well, how bad is it? And your error depends on several things. One is the F over D ratio. The deeper the dish is, the smaller the F over D, the more error you're going to get. This doesn't mean you can't make a deep dish, but you're going to have more error as you make it deeper. The shallower it is, the more accurate you are using the stress dish. And this kind of is obvious, but obviously the bigger the dish you are going to have, if you look at proportionally, the more error you're going to get when you're looking at an absolute error. So those are your big factors. I know, and I actually, this is obsolete. I got to change this because Mike and Monica, DL1YMK, you're here maybe? No? Yes. How high have you used your stress dish now? 6 gigahertz, so 6 centimeters. Okay, up. It's not good out there. Oh, it's not good, but it works. That's the point. It works. So I know that fairly large stress dishes have been used successfully up to 13 centimeters, and if you need to, you can even push it beyond there. And your dish is a pretty big dish. So if you make the dish smaller and you use stress principles, because the error is proportional length, it certainly offers the potential of using it. And you're a good example here because you prove the rule. It's certainly easier to assemble a stress dish than a full-size dish and weight-wise. So they're good for portable applications. This is another example here in looking at some of the problems here. And you're generally fairly insensitive to what you make the rods up of the dish out of, their cross-section and material. This was just an attempt, this RMS error versus F over D ratio, showing you the effect of F over D ratio, and that you do get a larger error as you go to lower F over Ds, but it's not terrible. This, again, is another curve, and I don't want to spend a lot of time on this, but it just shows you that as you get bigger, for a given F over D ratio, you start to get more errors. And from honestly, a very conservative figure, certainly a 12-foot dish it will give you very nice performance at 1296. A 40-foot dish in stress, probably not, but it would still be usable. Certainly on 432, you could go to a 40-foot dish, and from your errors, you get less than 1 dB loss of gain versus a perfect dish, which no one makes anyhow. And this slide here talks about, how do you make a reflector up using the stress dish concept. And if you're making a Parabola Revolution, which is illustrated over here, it's like making up a wheel. You have a bunch of spokes. You bend the spokes out somehow, and you can make up a reflector on this. I don't want to spend a lot of time here in terms of the different ways of making up a Parabola Revolution, because this talk, the focus is going to be on offset dishes. But this is an example of a 20-foot stress dish, which I used in many, many states and many, many locations, portable. I used to carry it on the top of this little car right over here all around the country, and used very successful. It handled the Faraday problem because you just take the feed. This is in Delaware, I guess. That's a long time ago, but I used that dish at least twice in Delaware. I guess, Russ, you were there one of those times. We went down to Delaware. And this dish still exists, still usable. I think the last time it was used was by Warren W2WD when he went to Nebraska. Anyone here remember the Nebraska expedition? There's only me, so it's a few years ago. But Warren took this to Nebraska with him. This is some details of the construction of the dish. It's made up of a bunch of pedals, and that's one of the secrets to make these things portable, is to have a bunch of pedals with a center section that you put the pedals in. They were made up so you can just push the pedals in. I'm sure in your arrangement, Michael, you have the same arrangement. You don't have to spend a lot of time with bolting and things like that. And then you just put it together and pull it up, and you have a dish. Okay. For 23 centimeters, we can get by with using smaller dishes, unless you want to have a big signal like Michael there. We start looking at small dishes, and we look at efficiency. One of the problems as you get dishes smaller is that the feed becomes tends to block part of the area of your dish. So you have aperture blockage. And one of the things that offset dishes have been sold for a long time is as a solution to the aperture blockage problem. I got to be honest. I put an asterisk. Sometimes you make assumptions. So in preparing, I did a bunch of calculations. You got to have a pretty small dish to have a problem with a significant loss from aperture blockage at 1296, and proportionally as you go higher. So even though people talk about this, this is not the real advantage of offset dishes. But there are other advantages, and it also offers, and this is, I think, the big advantage in the assembly and mounting, as I'll show you the dish. It may not be obvious how an offset dish does this, but there are advantages in this area here. So let's talk about what an offset dish is, because, again, there is a lot of misconceptions of an offset dish, because an offset dish is basically just a portion of a regular Parabola Revolution. You can really make an offset dish in any combination. Hannes showed a very nice example where he really used a hybrid between a Parabola Revolution and an offset dish. You're just illuminating a portion of the reflector. Your gain comes from the area of your reflector. You want to get as much area as possible. And the efficiency, the performance of that area depends on how well you distribute the energy across the area. What you really want to do is have your energy uniformly distributed across the area of your reflector and nothing spilling over the sides. And that's where that can't be done in theory. Or maybe in theory it can be done, but it can't be done practically. So you make a compromise in terms of your feeds, and that's where the compromise. I like to think of an offset dish as basically, at least most of the offset dishes, is a quarter of a regular dish. If you just take a dish and you take a quarter and you say, I'm not going to illuminate the whole dish, but I illuminate a quarter of the dish, and you can add a little bit on the sides to take care of the fact, as I'll show you, that from a feed point of view, in the typical pattern of feed, it's better to have this thing more elliptical than a slice of a pie. But that's what you should be thinking about, is a quarter of a dish. A key factor here is that the feed point of the dish does not change. It's always at the same point here. So you're just taking a quarter of the dish, but the feed point is always the same. One of the things when we talk about it, it does move the feed point, and this is where you get the advantage over blockage. It moves the feed point out of where your energy is going. And there's some value to that. But it also, as I'll show you, it moves the feed point down near the bottom of the dish, because there was also some points about some of us, not all of us, getting a little older and less agile. And part of the thing is climbing up to the feed point. Well, once you have an offset dish, now the feed point can be down near the bottom of the dish. And this is what I was getting at by the big advantage of using a offset dish. The feed point, of course, now the point here is this says feed points to the surface. What do I mean by that? Well, if this was a full dish, your feed would be pointing this way, right? But what you want to do is you want your energy here, so the feed now points to where your dish is. I think that's obvious, but it's an important concept to understand. It doesn't matter. The focal point is critical, but where your dish points is not that critical. It's just got to point toward the surface. So if you have a quarter of your dish, you rotate the dish up. Again, Hannes, I thought, did a very excellent job of showing how that works. In many cases, it can be the same feed, but we have to be careful. Generally, you needs a deeper dish for equivalent F over D ratio. What do I mean by this? What do I mean by needs a deeper dish? Well, it's really the feed. If I had a feed that's designed to feed this whole dish, it is going to not have enough gain. I need a higher gain feed because I want to illuminate at this distance, or approximately that distance, only a quarter of the dish. So I need, you could say, 6 dB more gain feed to feed a offset dish from Parabola Revolution. And that's an important concept. This curve, which is in the paper and available, shows you the relationship. If you had a full dish, okay, so this is the reflector, and this is the surface. You had if you had a full dish, you would have an F over D, the reflector would have an F over D of 0.46, let's say. You'd need a feed that's designed to feed a reflector with a 0.9 F over D. So you need a higher gain feed because it's a narrower area, less surface area you have to feed. On the other hand, if you started off with a reflector that had a 0.32, a deep dish, and this is, earlier I said the offset dishes tend to be deeper. So if you used a dish that had a 0.32 F over D ratio, what you would want here for your feed is about a 0.5 F over D ratio. It's about optimum for an IMU someplace between 0.5 and 0.6. So if you wanted to use an IMU feed horn for an offset dish, you'd want to start off with something down about in this region over here between 0.336 and 0.32, maybe a 0.35 F over D reflector designed to do that. And you can still get reasonably low errors using stress dishes, okay? So the bottom line over here, need higher gain feed. This is what I'm getting at because you got less area, narrower beam. Okay? So what does this buy you, so to speak? And this is where some illustrated examples of dish construction is. This example here, which is sitting right now in my backyard at home, I hope to do more with this before I got here, but time always never seems to be enough time. But this is sitting in my backyard right now, almost this exact picture. This is a 7.5-foot offset dish, okay? It's made up of 5 lengths of 1/2 by 3/4 inch. These are furring strips. I think here in Europe, in Australia, Japan, wherever you go, you probably can go to some supply store and you can buy lengths. It's really not, as I've tried to say here, it's not real critical what the size is, but lengths of wood. These can be also, they could be fiberglass, they could be poles, they can be bamboo, they can be aluminum, very nice. Why wood? Because it's cheap, easy to get, very accessible. I don't have to drive half a day to some aluminum place to find my material. And if it breaks, I can go out and just replace it. So you need 5 lengths of wood. The F over D here is about 0.3. Again, I was shooting to produce a reflector that matches something I have available. And this gives us a feed horn beam width of around 90 degrees. And this is just, I'll try and run through this quickly, but this shows you some of the details you need some sort of center hub, and you just attach the spokes to that center hub. The proper way to do this is to do some sort of system where these things just plug in, but with 5 of these, there aren't many screws to bolt, and so I just took the easy way out and bolted them in place. But if you really want to do something quick for portable, you can make these things so they just drop into little clamps and hold in place. Okay. Likewise, at the outside edge of this, you have a ring, and part of making this work is that you create a ring out of it can be the same material or slightly lighter material that you use for the spokes of your reflector, and these lengths, a molding strip, become the outside rim, and they just fold together. This, again, shows you this was designed for 1296, so we have just lengths of aluminum screening. You unroll the aluminum screening across the reflector, tie it down with little pieces of wire, and you're in operation in terms of your reflector. Again, a relatively easy, available material, readily available, not real high cost material. There's a lot of ways. This just shows you the feed. For this, and I've used a number of different feeds, this has a quad dual dipole feed. And why a quad dual dipole feed? Well, I made this up. I wanted to use it portable. And this thing is relatively small. You can carry it around. The IMU type feed or a scalar feed is bigger than the whole dish. That's the problem. And I'm still looking at other solutions on that. So this was a dual dipole. But this can be used with it depends what you have feed. This is just a picture. This was a mount. I actually made up a simpler mount for when this picture was made. Here are your 4 rods. Here's the feed. So this is something you can, if you want to go portable, very easy to do. Or if you want to operate from your home, but you don't want to leave it up all the time because of the XYL or the neighbors or things like that. This is something that you can take apart, assemble, put back together again. Now, the big advantage, an offset feed can be mounted very, very close to the ground. This is what I consider, in revisiting this, big advantage. This is actually the way this dish is sitting at my home. This is a mount I was using for testing, and I just have the dish laying straight down flat on top of the ground, because that's where, if it gets very windy or a storm comes up, it's the safest to be. And this is a better way of thinking about it. You could pick up a pivot point that's close to the ground. This becomes your dish, and when you are not using it, you can just lay the dish right on the ground. Your feed antenna is right over here, and the way I was mounting this is I was taking this feed pole and I was using that as my mount. So I would take this feed pole and I was mounting on the feed pole and then tilting it around. There's a lot of different ways you can do it, but the key thing is once you do this, and if you're worried about storms, you just take your feed right out of here. You let the pedals just hang on the ground unconnected when it's not in use, and you really have a relatively safe structure. You also can get to your feed very easily because when you rotate this thing over, the feed is right along the ground, so there's no difficulty, and you can make some relatively large dishes on this. I really wanted to build up something for 432 to illustrate this better than the 1296, and I never got around to doing that. That was my intention. I always have good intentions. Just speak to my wife. She will tell you that. But my intention was to build up a larger version of this for 432 but illustrates the same principle. So this is the concept. Again, some sort of centerpiece. I would make the centerpiece large to keep these small because there's a length as to how long a piece of a pole you can get or a piece of wood. This is a 20-foot, the equivalent of a 20-foot stress dish. So if I make this out of 4-foot pieces, or actually this is a 4x6 structure here, then these are about 16 feet, 16.5, 1x2, and that's available in the local hardware store or lumber yard, as we call it here. And this version here, I'm suggesting that you have 7 pieces, because this is a little bigger. You want when you get out here, you don't want too long a distance between your spokes. So for $12.96, you get by with 5, but here you really want a few more. And I was suggesting that you have a couple shorter pieces to fill the dish out, to make it up. You work quite well without that, but it's so easy to add. This is a side view, the same concept we were talking about before. Use the 5.5, the cross bracing here. This should be 5.5 feet approximately for the cross braces, the things up here on the top. One of the things I look at for portable is what the longest piece is, because sometimes if you're traveling on a plane or something, you can take this like skis, but there are limits as to how much you can carry, so you try and keep the longest piece as small as possible. By using this here, you really are starting your bending you can make it at a 1-inch offset, and if you work the curves out, you get a pretty good match. It's quite a good compromise. It actually can correct your curve on a deep dish by starting out and bending late rather than early when you go through the curve information. And as I say, when not in use, you just lay it flat on the ground. I'm not going to go through all these. It's just a list of the material. You can get that out of the book to make up a dish like this. But one of the key things is you don't have to be very skilled, and you can still make this work. One of the beautiful things about dishes is they're very forgiving. You cut a yagi a few tenths wrong, your elements, and you lose a lot of gain. You make a mistake on a dish a little bit, you don't see it. It's very, very small. So it's good it's very forgiving. So in conclusion, I'm talking about inexpensive and simple ways of making antennas for portable, and I don't want to put the option of using these in your home also for home use for 70 and 23, and quite frankly, I think these could be usable on 13 centimeters too, but in smaller size. The 23 centimeter dish provided 8 dB of sun noise, 3 dB more when I compared it to a really long loop yagi. And of course it was circular, allowed me to feed it circular, which is a big advantage because there's a 3 dB gain there. It's very easy to assemble, simple to mount, can mount the dish very close to the ground and store flat in the ground. So that's basically the talk here. Thank you.